இந்த வீடியோட தமிழ் வெர்ஷன் கமெண்ட்ல பின் பண்ணிருக்கேன். Make use of it. In this video, we will discuss the operating regions of MOSFET. Specifically, we will cover cutoff region, saturation region, and triode region. Triode region is also known as linear or ohmic region. And I will explain how MOSFETs behaves in each region. Transistors can act like a switch. It either block or allow current based on a small signal. They can function as either insulators or conductors depending on the input signal. Similarly, MOSFETs operates in these three different regions to control current flow effectively. In general, a MOSFET works in three main regions, which are cutoff region, saturation region, linear or ohmic region. Let's see them in detail. First, cutoff region. Think like this. You have a switch. If you don't press it enough, it won't turn on, right? Same thing here. In this region, the MOSFET is completely off. No current flows from drain to source, because the gate voltage is less than threshold voltage, which means we haven't applied enough voltage at the gate to form the channel. So what happens inside the MOSFET is no channel gets formed between source and drain. Since there is no path, so current can't flow. So the drain current is zero, or maybe just a tiny leakage. Think of a tap. Unless you turn on the handle enough, no water comes out. Same way, unless VGS crosses the V threshold, the channel won't open. In cutoff region, the gate voltage is too low, so the channel doesn't form. Since there is no channel, no current can flow. That means high resistance. Almost it's like an open switch, so no current flows. In cutoff region, the most important thing to remember is the drain current ID is zero, no matter what drain to source voltage is. Even if drain to source voltage is high, the MOSFET won't conduct because gate to source voltage is not enough to form the channel. Mathematical condition for this region is given by the formula ID equals 0 when VGS is less than V threshold. The drain current remains 0 regardless of VDS, which means no matter how much voltage you apply between drain and source. If VGS is below threshold, the MOSFET stays off. Now let's understand the practical importance of cutoff region. In digital electronics, we use MOSFETs to represent binary values, that is either on or off. When MOSFET is in cutoff, no current flows. So we treat it as logic 0 or off state. So no current means no signal, which means binary 0. And then it saves energy, that is power efficiency. Since drain current is 0, there is no power loss at all. Just think the power formula. P equals I square times R. If current I is 0, then P becomes 0 too. That means no heat, no power wastage. And that's what we want in low power design. So when it is off, it really stays off. No power drain. And next, switching applications. In digital electronics, we want fast and reliable switching. That means the device should clearly say whether it is on or off. So when a MOSFET is in cutoff region, it gives us a clean off. No current, no signal, no doubt. So it is either fully off or fully on. And that's why MOSFET are perfect for digital circuits. Now saturation region. In saturation region, the MOSFET is fully on and the drain current becomes independent of drain to source voltage. And this happens because of two conditions. First condition is gate to source voltage is greater than or equal to threshold voltage. The second condition is the drain to source voltage is greater than the difference between gate to source voltage and the threshold voltage. So what's going on inside the MOSFET is a conductive channel is formed between source and drain. The channel is pinched off at the drain end. This means the channel formed between source and drain is constructed or pinched off near the drain terminal. So this means the path inside the MOSFET where the current flows get very narrow near the drain side. It is like squeezing the water pipe near the end. So the flow is controlled there. And next, current is controlled mainly by the gate voltage, not the drain voltage. Once the path is pinched off, the amount of current flowing depends mostly on the voltage at gate, not at the voltage at drain. So changing drain voltage doesn't change the current much. Then MOSFET acts like a current source because the current stays nearly constant even if drain voltage changes. The MOSFET behaves like a steady current supplier controlled by gate voltage. So pinched off channel and current set by gate voltage makes MOSFET acts like a current source. In saturation region, the gate voltage is high enough to form a strong channel, but the channel gets squeezed or pinched off near the drain. Even if we increase the drain voltage, the current stays almost constant. So the MOSFET acts like a constant current source, not a resistor. In the saturation region, the current through the MOSFET, we call it as ID, depends mainly on gate voltage. So the drain current is approximately given by the formula ID equals 1 by 2 into the product of mobility of charge carriers, the oxide capacitance per unit area, and the ratio of width to the length of MOSFET channel multiplied by the square of difference between gate to source voltage and the threshold voltage. In saturation region, the drain current ID is mainly controlled by VGS and V threshold. Once the VDS becomes greater than VGS minus V threshold, the channel gets pinched off near the drain and the current becomes almost constant. After this point, even if you increase VDS, the drain current doesn't increase much. It stays nearly constant because it is now controlled by gate voltage, not the drain. Now, practical significance of saturation region. In saturation region, the MOSFET is fully on. This represents a clear binary 1 where maximum current flows. That's why it is perfect for digital circuits. The constant current characteristic of MOSFET in saturation makes them ideal for amplification applications. Here the current stays almost constant even if the output voltage changes. So it gives stable amplification, which is great for audio and signal circuits. MOSFETs provide a reliable on state in switching applications. The MOSFET gives a strong on state, which means reliable switching. This is useful in circuits where we need to control the current accurately. In analog circuits, MOSFETs can function as voltage controlled current sources. This means if you control the gate voltage, you can control the current. This is useful in many analog designs. So in saturation region, the MOSFET gives stable, predictable current. That's why it is useful in both digital circuits and analog circuits. In digital circuits, it is used as a switch. In analog circuits, it is used as an amplifier or current source. So from microprocessor to amplifiers, the MOSFET really shines. Next up, linear region. It is also referred to as triode region or ohmic region. In this region, the MOSFET acts like a resistor. You can control this resistance using gate voltage. The drain current ID increases linearly with drain to source voltage. That is, if you increase VDS, the ID also increases in a straight and proportional way. Suppose you double VDS, then ID also doubles. If you triple VDS, ID triples too. Now why this happens is, the gate to source voltage is greater than or equal to the threshold voltage. So channel is formed. But drain to source voltage is less than gate to source voltage minus threshold voltage. So the channel is still fully open from drain to source. Therefore the channel width stays the same and the current flows smoothly. Now what happens inside the MOSFET is, a conductive channel is formed between drain and source. This means there is a clear path for current to flow. The MOSFET is on, so electrons or holes can freely move from source to drain through the channel. Next, the channel width remains constant throughout its length. That is, the thickness of the channel doesn't shrink near the drain. It stays same from start to end, like a uniform pipe. After that, the MOSFET acts like a variable resistor controlled by gate voltage, which means the resistance of the channel depends on how much gate voltage you apply. So in linear region, the MOSFET gives a smooth and steady channel from source to drain. No pinch off, no blockage. So the gate voltage acts like a volume knob. The more you turn it up, easier the current flows. That's why we say it as the MOSFET behaves like a variable resistor. So higher gate voltage creates a wider path for current, and resistance goes down and currents goes up. And here is the equation. It is given by the formula ID equals mobility of charge carriers multiplied by oxide capacitance per unit area multiplied by width to length ratio of MOSFET multiplied by the quantity of gate to source voltage minus threshold voltage and multiplied by drain to source voltage minus half the square of drain to source voltage. This relationship holds true when drain to source voltage is less than the difference between gate to source voltage and threshold voltage. Now the drain current increases linearly with the drain to source voltage. That means if you slowly increase VDS, the ID also increases steadily like a straight line. Therefore the rate of increase, that is the slope, depends on how much gate voltage you apply. Now let's understand the practical significance. In this region, the MOSFET can be used like an electronic on or off switch. It can be turned on or turned off by changing the gate voltage. Next, MOSFET behaves like a resistor in which the resistance can be adjusted using the gate voltage. That is like a knob for current flow. Next, it is used in power supplies to provide smooth voltage control because the MOSFET adjusts the current based on input and load conditions. After which, it is ideal for amplifying small signals in analog circuits. That is, the current changes smoothly with voltage, which helps in clean amplification. Then it is used in transmission gates. Transmission gates are special type of electronic switches made using MOSFETs. They are used to pass analog signals like sound from a mic or voltage from a sensor. When the switch is on, the signal flows through it smoothly without changing its shape or losing strength. That's why they are used in audio systems, sensor circuits, and mixed signal ICs. Therefore, in this region, voltage and current increases together in a smooth straight line. That's why MOSFETs are great for analog circuits. Here is a summary table of 3 operating regions of a MOSFET.